the connection in series mode as well as parallel mode. Okay, so during series configuration, we can see that the plug would be connected to storage system, then again the inverter, okay, traction motor, and then to this operation. So in that particular scenario, the connection from IC engine generator would be only in this particular direction, from IC engine to the generator and then to the traction motor. So this connection would not be, taking place, and this would be taken care by this power split device. Okay, the power split device is going to ensure that the IC engine output is fed to the generator and the generator output is connected to traction motor only. So this is going to realize the series operation. So this is something that we should understand. Okay, so this is the first part. Next, when I want parallel operation at that particular in that particular instance, I will ensure that this connection which was previously not present, this connection which was previously not present would be brought into action. Okay, so now in parallel connection, this connection would be brought into action. Okay, on the other hand, the power split device would ensure that this second this second connection is not present. So this connection would be removed in case of parallel operation. So IC engine, generator, transmission, and wheels. So this would be the first option, and the second is from the energy storage system, inverter, traction motor, and then to transmission and wheels. So that would be the second scenario. Okay, so again, this role would be played by the power split device. The last type of topology that we need to understand in this case is related to fuel cell electric vehicle. So when we're speaking about fuel cell electric vehicle, we normally say that the chemical energy is converted directly into electric energy. So the power source has now changed. So when we are speaking about chemical energy, we are trying to extract energy from hydrogen. Okay, so the reaction also it's very simple. We are going to take hydrogen and oxygen as input and the byproducts. Okay, the byproducts would be water in this particular case and energy. Okay, so when we are making use of a fuel cell based system, we need to understand that the input chemicals to this particular system are hydrogen and oxygen. Okay, and the output is water and energy. Okay, so they are governed. This amount of energy is generated by the law of Gibbs free energy. Okay, so Gibbs free energy equation as per thermodynamic laws, it is shown. And normally, if we have seen in our premier classes, elementary classes, that the side is called as product side and the left hand side is called as the reactant side. Okay, so the amount of energy is given or given by this particular simple equation. Okay, so delta G is going to be equal to summation of GI of products minus summation of GI of reactants. So products minus reactants, that difference is going to be the energy itself. Okay, so we are going to have this type of system. So the output from the fuel tank is further connected to it's connected to generator. So there is another connection which is given over here, generator. And additionally, we do have a IC engine. So this is a backup. Okay, so IC engine is a backup which is used over here because in emergency we have to start the operation of vehicle with the IC engine. Okay, and as the reaction progresses, these are slow reactions. Okay, so we need to understand that these are very slow reactions. So the energy would be generated, the battery would be charged. So for long time operations, they are going to be economic, no doubt about that. But under emergency, we always have to make use of the IC engine based system. Okay, so the emissions from this vehicle is also water, which is again a clean source. So we can see that the emissions are substantially reduced. So it's a clean source of energy. So fuel cells vehicles are also looked upon as alternative vehicles to IC engine systems. Next, the electric energy is used for propulsion of motor as well as for charging the battery. And as I said, the thermodynamic voltage which is generated is through this particular reaction using Gibbs free energy equation. So this is something about fuel cell electric vehicles. And then, so the part which we have studied up till this particular moment are shown over here. So we have shown the component of series vehicle, we have discussed parallel, we have seen series hybrid and complex hybrid, which included the fuel cell. Okay, so in series, we have seen that the electric motor is itself the main component. Okay, the IC engine will be only used, it will be only used to charge the battery whenever the battery of battery is energy is going to be almost depleted. So during that part, the IC engine would be brought into action. When we are speaking about the parallel components, there are two sources and they are independent. Okay, so the transmission has independent connection of the mechanical component and the electric component. Okay, so either of them they can be used. If we are speaking about series parallel configuration, then we are having a power split device. Okay, and this power split device, it can be used to realize a series operation or parallel operation, any one at a time, obviously. Okay, and the last we can see that it's a complex hybrid, means it's employing the IC engine based system, it's employing the fuel tank system. Okay, in addition to the electric components which are shown over here. Okay, so this was the first part that I wanted to tell. Okay, and then there was a comparison, there is a comparison over here which is of pure electric vehicles, hybrid electric vehicles and fuel cell electric vehicles. So the battery EVs are pure electric vehicles. The second component which is shown over here is the hybrid component. Okay, and this again it can be either pure or it can be hybrid. Okay, so therefore it's categorized as a fuel cell component. Okay, so the propulsion system is a system which is going to be used for generating the tractive force and making the vehicle move forward. So that's the propulsion. So here in case of pure electric vehicle, the electric motor drives, which is the power converter and the machine, which will be together forming the drive assembly. So that is the main component. In case of hybrid vehicles, it will be employing the electric component as well as the mechanical component. So both motor drive as well as the IC engine system, they would be present. Next, if you speak about the fuel cell, then again it's a type of series system. That's why we only find the electric motor drives. Okay, the IC engine, if at all it is present, it would be used to charge the battery. Okay, so that's what we have seen in the block diagram as well. Next, the energy system over here is battery or the ultra capacitor. While if you talk about hybrid EVs, then the power source will be battery, then the fossil fuel. Okay, so fossil fuel is going to be driven by it's used to drive the IC engine generating unit, so that is present. Okay, and in case of fuel cell, we are going to have energy system as a proton exchange membrane based system for generating the energy. So fuel cell, then the battery for increasing the power density and so on. So they will be present. The third point of comparison over here is the electric energy source, sorry, energy source, not electric energy, energy source. So in case of pure electric vehicles, the battery grid charging facilities they have to be present. While in case of hybrid fuel, it has to be either the fossil fuel or the grid charging facility over here. Okay. While in the case of fuel cell based system, we can have the hydrogen based system or the hydrogen production and transportation infrastructure. So typically this is very important because hydrogen by default is a explosive element, so it has to be handled very carefully, and therefore hydrogen production and transportation infrastructure has to be done in a controlled environment. Okay, even the transportation has been is to be done with a great deal of care. Right, so these type of fuel cell EVs are going to have these two infrastructures requirement. Then we are going to speak about the characteristics. So it's going to be zero emission. Here the word very low is used because if it's a hybrid, then as compared with pure electric vehicles, the emission would be lesser. Next aspect that we need to discuss about is the higher energy efficiency. So that is there. Next, we are having independence on crude oil. Complete independence is possible in case of pure electric vehicles. Okay, so that is there. Next, initial cost is higher because the cost of battery is there. At the same time, battery maintenance is also there. So that is coming into battery management and battery related issues. Next, charging facilities, they have to be there. We need charging stations. We need the infrastructure to handle the batteries. Okay, to maintain the batteries and the type of power. So AC level 1, AC level 2, DC level 1, DC level 2. So there are different charging ratings. So as per the requirement, we need to configure the electric vehicle supply equipment. So that is there. Okay. So these are the issues which are being dealt. Okay. And our government has taken a lot of initiatives to expedite solving of these problems at a very fast rate. So sooner or later, in a couple of years, we can see this will be spread out in our country. Okay. The next, in case of hybrid, there is a the dependence on fossil fuels has been reduced on a considerable basis, but still we have to take into consideration the battery sizing and management. Okay, so battery sizing means we have to take care about how much should be the sizing of the vehicular battery and how much should be the sizing of mechanical IC engine based system. So previously, if it was a 1200 cc vehicle, then in case of hybrid system, we need to discriminate. We need to distinguish properly that the mechanical component, it should be how much, and if there is electric component, that should be how much. So in hybrid systems, we have to properly design the battery sizing as well as the sizing of IC engine. So these two components, they would be playing a very vital role. And at the end, if we consider the fuel cell systems, we have to consider the infrastructure for generating hydrogen. Okay, so that would be there. So at least in India, we are very at a primitive stage or initial stage so far as hydrogen infrastructure is considered. So sooner or later this will also be considered, but now this is a major challenge so far as our country is considered. And then the fuel cell life cycle and reliability, as I said, it's a slow reaction. Okay, so you have to make use of a IC engine based system so that we can cater to the emergency energy requirements while driving the vehicle. Okay, so this is the very basic part that I wanted to tell so far as the topologies are considered. So I'll take a pause over here and I will ask if you people are having some doubts. We can briefly have a discussion for around 5 minutes. Okay, so from your end, I would appreciate if there are certain doubts from your end, we can have a brief discussion and then I can go back to the next part of my series. Okay, so I hope you are getting whatever is being taught right now. So if there are any doubts, you can please raise it so that I would be happy to address them because we have covered the topologies. So I wish to take a small, interactive session and we can have understanding. So how much you have followed. Okay. So if there is no interaction from your end, I can, pose couple of questions and you can answer those in the chat box. Okay. So if I wish to answer whether I understand whether you have understood the difference between series and parallel type of electric vehicle. So what is the key difference in case of series and parallel electric hybrid vehicles? So can anyone just type in the chat box or they can unmute themselves and answer the question? Okay. So anyone. just to make sure that you have followed whatever I've taught or not, I just want to ask whether you have understood the key difference between series hybrid electric vehicle and parallel hybrid electric vehicle. Anyone? You can type in the chat box. So shall I continue forward or shall I re-explain the part again? If there is any doubt, you can raise it right away.
Please, please continue, sir.
Okay, I'll continue. So the next part that we need to understand is about degrees of hybridization. So there is this word coming as degrees of hybridization. Okay. So when we talk about degrees of hybridization, we are going to talk about the extent. We are going to talk about the extent to which the electric components are present. The extent to which electric components are present in the system. So based on that, we are going to categorize them as micro, mild, okay. Then we are going to have a full hybrid system, plug-in hybrid system, and so on. Okay, so we will be categorizing them as micro, mild, full, and plug-in hybrid systems. So when we consider a micro hybrid system, then it will be satisfying only one of these conditions. So these are the conditions, okay, that are to be met. These are the conditions that are to be met when we are speaking about the degrees of hybridization. Okay, so when I'm using the word micro, I am only going to say that the vehicle can be, start and stopped using the electric component. So that's a very basic or primitive example. Okay, so this is something that we should definitely understand so far as micro hybrid system is considered. When we speak about mild hybrid component, when we speak about mild hybrid component, it is going to be in a position to start stop. Okay. Next, it supports regenerative braking. It supports regenerative braking. So when I'm using regenerative braking, I'm always saying that there is going to be a bidirectional power flow. Okay. So bidirectional power flow would be there, and we can charge the battery during runtime. Okay. So it supports battery charging during runtime. So this mode is supported. Then we say that okay, it's a mild hybrid. Okay. At the same time, we can say that the electric motor would be assisting a combustion engine. It would be assisting a IC engine based system. Okay, but practically, if you understand the vehicle which are present in the market, in Indian market, if you consider which type of vehicle is categorized as mild hybrid in our Indian market, I can tell you that there is a vehicle from Maruti which is called as Grand Vitara. Okay, so this vehicle is there, and then we are having High Rider from Toyota. Okay, so these are mild hybrid cars. Okay, so these two cars, they are mild, so hybrid, so mild hybrid, as I said. So High Rider is there from Toyota and Grand Vitara, both of them. Okay, so they have improved fuel efficiency. When we use mild hybrid vehicles, then we can say that it uses an electric motor to assist the combustion engine. Okay, so if you see both these vehicles, the mileage is around, okay, 21 or 22. So around 21 to 22 is the mileage which is increased, even if the capacity is around 1500 cc. Okay, so for a vehicle with rating of 1500 cc, we are getting a mileage of around 21 to 22 per liter of petrol, which is really nice. Okay, typically for a 1500 cc, if it's a IC engine based vehicle, the average would be around 12 to 13. Okay, so when we are using electric component and battery component together, we can get a substantial increase in the mileage around 8 kilometers per liter. So 8 kilometers per liter. Yeah, that's correct. Okay, so that is mild hybrid. So this is something we should always keep in our mind. The next type of vehicle that we need to understand is a full hybrid. Okay, so when we consider about a full hybrid electric vehicle, we are speaking about this four conditions. So this three conditions, they're already present, no doubt about it. But in addition to that, a fourth condition is considered, wherein we say that okay, the vehicle is in a position to carry or generate the entire tractive force using the electrical component. Okay, so using the electric component, we are in a position to generate the entire tractive force. So that part is something we need to understand. Okay, so as I said, the tractive force is the power which we want to move the vehicle forward. Okay, so for moving the vehicle forward, we have to require certain set of conditions. First of all, I have pre-decided, okay, I want to run or operate the vehicle at 40 kilometer per hour or something like that. So that is one such input. So for that, some force needs to be calculated. Okay, so let us call that force value as like F1. Okay, so this is the force or the energy which can be quantified for generating uh, speed of around, let's say, 40 example. So this is only an example, I want to take this example. So in addition to that, I will have to consider all the opposing forces. I will have to consider all the opposing forces. Now what are the opposing forces? As I said previously, it may be the aerodynamic drag, it may be the rolling resistance, and it can be the hill climb resistance. So we'll consider these equations one by one, okay, as we progress ahead. After that, in plug-in hybrid vehicle, we are going to have EVSC. Okay, EVSC. So this full hybrid is going to be a series HEV. Okay, series HEV. So we will be saying that this is a series HEV, and the IC engine based component would be present, and that would be in a position to generate power enough to charge the vehicle battery, and we can drive it. Okay, so we can categorize them. And in case of plug-in hybrid electric vehicle, we can have this component electric vehicle supply equipment is present. So we will be in a position to charge the batteries from a wall outlet. We will be in a position to charge the batteries from a wall outlet. So this is very much important. Okay, so we can see that there is a electric vehicle supply equipment, and using the electric vehicle supply equipment, we can charge the battery. So if this condition is satisfied, we say that it's a plug-in hybrid vehicle. So this is something we need to understand. Okay, that is about degrees of hybridization. Now the next part which we are going to consider is about the energy loss, and this energy loss comparison is going to be done in between IC engine based system and EV based system. So these two systems, they are present. Okay, so let us understand. So now fuel tank, if we say that if 100% energy is present over here, okay, then how much amount of energy would be reaching at this destination? Okay, so net, if we start with 100, then how much energy is going to get dissipated at different parts that is something which we need to talk about. So the very first part that we need to understand is about engine efficiency. So here, if we are considering the engine efficiency, we can see that the losses in the engine are around 76 and this is around 8%. Okay, so we get 16%. Okay, so can someone tell why it's coming over here as 16%? So it's plain mathematics. So it's 100 minus 76 minus 8. Okay. So this is the loss which is taking place inside the engine, and this is the standby loss. So whenever I'm just starting the vehicle, there are standby loss associated, and that is amounting to 8%. So the fuel, if it is having a tank is 100% efficiency, then the net energy which is fed to the drive system is going to be around 16%. Okay. So again, if we talk about driveline system, then the losses which are present in the driveline are 3%. Okay. So this 13% is going to be, 16 minus 3. So this 16 is coming from over here, and this 3 is coming from the driveline losses. Okay. So the fuel tank, if it is 100%, 76% are lost inside the engine, 8% are in the standby. So effectively we get 16%, again 3% are lost in the driveline. So effectively we get 30. Okay. And then we are also having the variable losses. Okay, so we do have the variable losses. And these variable losses, they are going to amount 3%, 4%, and 6%. Okay. So they are going to have 3, 4, and 6%. So aerodynamic drag. What is aerodynamic drag? So if we are having a electric vehicle, okay, if we are having an electric vehicle, then we can say that the aerodynamic drag is going to be the force. It is going to be due to the air pressure. There would be air pressure, and this force would be creating a drag. So this would be creating a drag force on the vehicle whenever the molecules of air they are going to be colliding. Whenever the molecules of air they would be colliding with the vehicle surface, front surface. Okay, so this is the frontal area. So the frontal area would be subjected to air, and the aerodynamic force is going to be opposing force because of this vehicle 1 by 2 rho into AD into V square. Okay, so this is the equation where V is going to be the speed of vehicle. Okay, and there are different, A stands for the frontal area and rho is a constant. Okay, so more is the frontal area, higher is going to be the aerodynamic drag. Similarly, rolling resistance. So when we talk about rolling resistance, then the rolling resistance is going to be contributed to the weight of vehicle. Okay, it is going to be due to the weight of vehicle, and because of weight of vehicle, it would be exerting force on the vehicle, and that would be generating this rolling resistance. And the third one is the braking. So if we are going to apply braking, there would be losses as well. So these are dynamic losses which will be changing as per the drive environment or the drive cycle. So the next part which we need to address is related to highway driving. Okay, so during highway driving, we can see that the standby losses they are made equal to 0. Okay, so previously we were having the standby losses as 8%. Now that losses they are made equal to 0. So on the long run, we say that the standby losses become into 0. So the average increases slightly. So this is something which we are already aware of. Okay, so now you can see this 100 minus 77 is amounting to the 23%. Okay, it's amounting to 23%, and that again the driveline losses they are going to increase to 4% because the vibrations they are going to increase as the speed they are going to increase on the long run. So slightly it has increased, and then the 19% efficiency is present, which is available is again subjected to this variable losses, and those variable losses again they are same: aerodynamic, rolling, as well as braking. So based on the speed of the vehicle, these losses they would be changing in the real time basis. Okay. Now, if we are using hybrid systems, if we are using hybrid systems, means both components are present, electric as well as mechanical. Now, what would happen? So in the micro hybrid, this part would be eliminated. So standby loss completely eliminated. Okay. So 100 minus 76 directly we can say that this value is going to change. So previously this was 100 minus 76 minus 8. Okay. So 16 plus 8, here we are going to get 24. So 24% would be there definitely. Okay, so 24, this 13% which was present previously is going to be 24 minus 3, which would be 21%. We can see that the net improvement is from 13 to 21%. So that's the advantage of making use of mild component. Okay. In addition to that, this 6% is further added over here because in braking we are making use of regenerative action. Okay, so regenerative action is going to inject the energy back again to the battery. So that would be, reduced. So this is reduced substantially. This was eliminated and this is reduced to a great extent. Okay, ठीक है. In addition to that, the engine loss is also reduced because in case of hybrid system, we are going to downsize. So previously, if it was 1200 cc, then the now new configured hybrid vehicle would be brought down to around 1000 cc or lesser than that, depends on the manufacturer. So vehicle would be downsized, so the losses would also be reduced proportionately. So this is something we can understand very easily. Okay. And if you are using plug-in electric vehicles, then this engine loss will also be eliminated. So this can also be eliminated directly. So standby loss as well as the engine loss is eliminated. Okay. So if you see this diagram, now previously from 100%, we are going to have only 10%. So this are core as well as copper loss. So we are having both these losses and that is amounting to 10%. So the net energy which is left over for us is 100 minus 10, which is 90%. Okay. Inside this drive line, we are having 40% losses. So 90 minus 14 is 76%. Okay, so considerable increase in energy. Considerable energy increment is visible over here, and that is around 76%. So that is around 76%. So previously it was 23-24%, and now it has changed to 76%. Okay. So that is something we can understand. Okay. So in addition to that, we can have aerodynamic, rolling and braking losses. So they are going to be dependent on the dynamic conditions. So that is the vehicle related losses. So I hope you have understood. I hope you have understood the efficiency scenario in case of electric vehicles as well as the ICE engine based vehicles. So we can definitely see the mathematical comparison of energy efficiency in the electric vehicles in hybrid vehicles. So we have seen how the standby losses they are going to get eliminated in micro hybrid, and that will contribute to overall increase in efficiency. Further, will be engine downsizing, that will again increase the efficiency. Okay, so like that we have talked about the efficiency improvement. So I guess Siddharth Dhere has raised his hand. I guess he might have some doubts. So yes, Siddharth, if you are having any doubts, you can ask me. Others also, I hope you have understood. You can type in the chat box whether you are following whatever is being taught or not. So is it clear? The next point which I had covered just now. Is it understood, everyone? Shall I continue?
Yes, sir. Please.
Okay. So Siddharth, if you are there, you can ask your doubts as you have raised your hand. You can unmute at any point of time and you can ask your doubt. The next aspect that we need to talk about is well to wheels efficiency. Okay, so the next is related to well to wheels efficiency. So well as in the refinery. So when we are considering the refinery, it's a oil well, okay, and then we speak about the well to wheel. So this is wheel efficiency, well to wheel efficiency, okay. So this is something we need to understand. So whatever is present, energy is present at the input side, how much energy is present at the output side, okay. So here we are going to consider the electrical section, okay, and here we are going to consider about the fossil fuel section, okay. So please let us try and understand. So if you see the refinery or oil section, we can say that the generation efficiency is around 33%. Okay, so we can have that this is 33% efficiency. Okay, transmission efficiency is 94%. So effectively, we are getting 31% over here. Okay, so if 100% again it is present over here, after generation we are going to have 33. Okay, and then 94% of 33 is 31. Okay, so we can say from the transmission side, okay, from the transmission side the efficiency is 31%. Okay, so the efficiency is 31% at the transmission side. So this is the first part that we are trying to understand. Okay, next, if we consider the fossil fuel section, okay, so sorry, further we are having well plug into wheel efficiency. So this 23% we have already seen. So how it has come in the previous slides, we have seen that overall vehicular efficiency we are observing it as 76% in case of electric vehicles. So I can say that 76% of 31 provides us the value of 23. So that's a very plain mathematics that we can understand. So effectively, in case of electric vehicles, the efficiency comes out to be 23%. If we consider the same scenario in case of you know fossil fuel based system, if we are having 100 over here, then here we are having 82%, okay, and then 98% of 82, if we calculate mathematically, it gives us 80%, okay. And then when we are speaking about this pump to wells efficiency, so this also we have discussed right now. So that came out to be 16%. So 16% of 80, it comes out to be 13. Okay, so finally we can see that the electric vehicle is at 23% and the IC engine based system is at 13%. So we can again say that the electric vehicles are more efficient as compared with the fossil fuel or IC engine based vehicles. So this is something we need to understand. All right. So overall, we can see that on one side we are having 23% and on the other hand we are having 13%. So now what are the major challenges? What are the major challenges that we need to address in case of electric vehicles? Long charge times, then there is high initial cost. So the cost at the initial time which we have to invest is very high. Okay. The next part is battery life, and finally we have to talk about the consumer acceptance. So there is a range anxiety so far as consumers are concerned because the charging infrastructure is still being developed. Okay, soon it will be reduced. The consumer acceptance will be increased, and so the solutions, we can have the accepted limited range is 40 minutes per day, and this is just a general survey. Most cars are parked for 23 hours of the day anyway, so this is quite suitable enough. We can couple solar as well as electric together, and we can further increase the efficiency. Okay, so this is something we should think about and go ahead for procuring electric vehicles. So there are alternative approaches called as battery swapping in case of emergencies. So we can replace the batteries in case of emergencies, and we can go ahead if we want to travel long distances or if it's a critical situation. So that approach is there. Okay. So battery swapping, there are specialized agencies which they take care of this swapping of batteries, and in very smooth transition way this can happen. Okay, so we can have this difference. So now the type of batteries which are present over here are lithium sources. Lithium is very abundant. Okay, so that is the reason why we make use of lithium and lithium polymers. Okay, in addition to that, the weight to volume, weight to volume ratio is higher as compared with any other type of battery, lead acid batteries or tubular batteries or any other type of batteries. If we consider, then it's very much advantageous when we consider lithium source as the prime element. Next, as compared with the other type of batteries, this has a very less maintenance. This is very less maintenance. Then there, by using BMS systems, we can improve the battery life. And also there are alternative battery chemistries of lithium polymer compounds which are further on the higher side of specific energy and weight to volume reduction. So that is again a good advantage. Okay. So that's the reason. So initial cost, we can have these like power purchase agreements is there. There are going to be companies like Adani and Reliance who are going to be stepping in this market, which will help us to have these kind of power purchase agreements in near future. So that would be one such part. So that is definitely going to be there. The next part that we need to address over here is wireless charging system. So that is another solution in order to address one of the challenges. So in order to address the issue of range anxiety, we can have this kind of solution. This kind of alternative approach is going to be present. Okay. So we definitely see that these type of systems. Okay, I will just show you the image first. So this is the wireless charging system. Okay, so this is a wireless charging system. You can see that this type of coils, high power coils, they are present and they are going to transmit power wirelessly. Okay, so if you see the circuit diagram now, okay, so here we can definitely see that this coil was shown in the it was present on the road as you have seen in the slide which I have just shown. Okay, in the road there is this circuit which is present already. So AC power, which is single phase or three phase as per our requirements, that is present. Okay, so this AC to DC conversion is done, and finally we are converting the DC into high frequency AC. Okay, because we want to transmit the energy in a wireless fashion and we want to have high energy density. So for that we are converting the DC to high frequency AC. and then the primary compensations are nothing but the filters which are used. Okay, and then we are transmitting the energy. So this is the location where we are transmitting the energy. And again, at the receiver side, we are having secondary compensation. From the secondary compensation, we are having a controlled inverter, sorry, controlled rectifier, which will be charging the battery. So this circuit is being realized. It is being realized in countries like Israel. Okay, so it's already present over here. So these are called as smart roads. Additionally, there are these type of systems as well present in Indian scenario. We have seen these kind of systems in our railways, wherein the pantograph is used for charging the batteries of locomotives. Okay, electric locomotives, they are present and they are charged by the pantograph. So similar type of arrangements, they can be employed for public transportation buses, and by using that we can easily reduce the issue of range anxiety. Okay, so that is there. So this is something we need to understand. So I hope you have understood this. So up till this point, if there are any doubts, you can ask me. If there is any doubt up till this particular point. So we have seen topologies, we have seen different types of efficiency conversion mechanisms, we have seen in pure electric vehicle, we have seen in case of hybrid electric vehicle, then we have also seen well to wheel efficiency. So all these aspects we have covered. Okay, and then we have addressed the challenges which are present in the electric vehicles and the means to address those issues. So if this is understood, then you can raise the doubts. Okay, if it is clear, then I can move on towards the next slide. I would expect some kind of interaction from your end. Okay, so first part of my explanation is
No, sir, no any doubts. First, I would like thank you because of in a short period you just accept our institute invitation for FDP, and thank you from all our institute. And I declare that today's session is concluded. Thank you, sir.
ma'am, actually ma'am, there is one more point which I had to cover. There is still remaining.
Okay, sir. Sorry, sir.
I'm
Continue.
sharing the second slide.
Okay, sir. No problem.
Okay. So the first part related to topologies is covered. Now I'll be explaining the electric vehicle charging infrastructure. So that part I will just explain it. So I've started sharing my screen. Is the screen visible?
No, sir.
Okay, I'll retry it once again. So please let me know if the screen is visible.
Okay, sir. Now it is visible.
Okay. So let us talk about electric vehicle supply equipments. We have been, discussing about this since the beginning of the session. So electric vehicle supply equipment, or in short, we can say that electric charger. So this is something we need to understand because we are having EV bikes, we are having, EV four-wheelers. So we need to understand what is the difference between the EVSE. Okay, what are the charging standards which are supported by different electric vehicles? So this is something which we need to understand. We'll finish it within 15 to 20 minutes. So now EVSE, if we consider, EVSE is equipment that is going to deliver electrical energy from electric source. Typically it will be the power source which is present in our house or a charging station in order to charge the electric vehicle energy storage, or I can simplify by saying a battery. So EVSE, it is going to deliver the required amount of electrical energy to the battery of electric vehicle. The next part that we need to understand is this electric vehicle supply equipment would be providing us either AC or DC power depending on the type of vehicle we have procured. Okay, so it is not only that it is going to provide us AC, but it can provide us AC or DC. So this is something also which we need to understand. Okay, so that's the second point which we need to understand. The third point that I want to tell you is about EVSE is regarding communication. The EV also plays a very important role of communication. So it establishes a steady communication between the battery system or the BMS system of the vehicle and the power source which is present at the charging location. So it is going to generate a plenty of handshaking signals, and it tells us whether the vehicle is being charged properly or not. If there are any fault conditions, it will stop the charging. If the vehicle is being charged, then it will also give us the indication of how much time is required for charging the battery. So how much remaining time is present. Okay, all these things, they will be communicated in real time by the EVSE. Okay, so now the next part which we need to understand is the classification of EVSE. So if you consider the classification, we are having electric vehicle supply equipment as AC charger, DC charger, or CCS. So CCS is combined charging system. So AC charger, if it is present, then it can be type 1 or type 2. If it's a DC charger, again it is going to have a CHAdeMO or GB/T. Okay, so it would be CHAdeMO or GB/T. And finally, if it's a combined charging system, means it is going to support AC or DC. Both of them, they will be present, AC, DC. So in that case, the word combined charging system is used over here. Okay, so if we talk about EVSE, we are having AC charger. It will further be bifurcated as type 1 or type 2. If we are talking about DC, it is a CHAdeMO or GB/T. In case of CCS, it will be supporting both AC as well as DC voltage ratings. So now let us talk about the first type, okay, type 1 AC. Okay, so this is type 1 AC. So if you see the power which we need to, which we can get at the max is 7.4 kilowatt. Okay, 7.4 kilowatt, and the current which can be supported to the charging system is around 32 amps, so which is quite sufficient enough. Okay, so for all four-wheeler systems, it's quite suitable. Okay, so AC chargers up which are having motors up to 7.4 kilowatt and 32 ampere support, they can be used with type 1 system. Okay, it's widely accepted in the US countries or American countries. If you talk about the European countries, then they make use of type 2 systems. Okay, so these type 2 systems, they are have increase in power requirements from 7.4, it's increased to 44 kilowatts. And if you talk about the currents, it's going to support up to 63 amperes, and it's a three-phase system, so they are going to support three-phase charging up to 63 amps. So here the charging was by single-phase systems, and here the charging is by three-phase systems, and so the charging time will be reduced drastically if we are making use of type 2 systems. So that is there. So that's the next advantage we can see. So the vehicles which are supporting type 1 as well as type 2, they are shown over here. So that is there. Next, if we talk about DC charger system, then we can see that CHAdeMO is present and GB/T is present. So GB/T is, has originated from China, while CHAdeMO, if you see, it's originated from Japan. So here again, the power that we need to understand, or in case of CHAdeMO, is 1000 volts and 400 amps. Okay, and in case of GB/T, which is in the Chinese segment, we are having 950 watts and 250 amps. Okay, so more or less we can see that the voltage rating is same, but the current rating, we can see that in case of CHAdeMO it's 400 amps, but in case of GB/T it's around 250 amps. Okay, now I would like to highlight another important point is that in case of Indian market scenario, most of the DC chargers, they are from GB/T. So you can see that in mm, as in Bharat chargers, there is a segment called as Bharat chargers. They employ GB/T, right? So as an example, Mahindra Electric, they are widely using GB/T. Okay, and then for communication, all these both these components, they are making use of CAN protocol. Okay, so the communication protocols, as I said, CAN protocol is there. Then there is a 7-layer OSI model. You might have gone through it at some or other point of your engineering. So the 7-layer OSI model, it comprises of physical layer as well as data link layer. And if you see the SAE standards which are used by manufacturers, they are making use of J1939-11 or J1939-21 for designing this you know arrangement of EVSE. Okay, the sockets and the design of the sockets and the plug designs, they are done with the help of these SAE standards that we need to understand. Okay, so that's the. In addition to that, if we consider CHAdeMO, then CHAdeMO is making use of IEC 15118-3 standard and ISO standards. So both either of these standards, they are used. Now the charging sequence flowchart, which is typically important and that needs to be understood by all of us. Okay, so at some or other point of time, you might have gone through charging of a two-wheeler EV or a four-wheeler EV. So during all the charging operation, these are the operations that are happening. Okay, so if you see, there are two main segments. There are two main segments. One is the charger side and the another one is the vehicle side. Okay, so there is a fine line. So this is the left hand side. I let me call it as the left hand side, and this is the right hand side. So this left hand side will speak about all the communication signals or the handshaking signals from the charging side, and in the vehicle side we are going to consider all the signals from the vehicle side, all the signals from vehicle side. So at the very beginning, the charger is going to generate the start of charging signal. So if you see this socket, we are going to have start of charging signal from the D1. Okay, so if you see D1, I'll take a laser pointer so that it becomes easier for you to understand. So this D1 is present. So the D1 in the connector is at this particular location. So from this we are going to initiate a start of charging signal. Okay. Now at the vehicle, it is going to recognize this charge of charging. So this F signal, it is going to recognize that, okay, I want the charger is connected and there is electric connection established properly. So there we will be recognizing this F on signal. The next part is the vehicle. Okay, so the vehicle is going to generate series of control or handshaking signals. These control signals or handshaking signals, they are going to tell us, okay, the battery capacity is of like 2.2. Okay, then maximum voltage is around 200 volts, then the current rating is around 30 amps. So all these signals, they would be sent from the vehicle to the charger. It will be sent from the vehicle to the charger. Okay, and then there would be a compatibility check. Okay, so the charger is going to check whether it's compatible or not. Okay, why compatibility check? Okay, if you are using the dedicated charger given by the company, it is straightforward, that is going to happen immediately. But if you are charging at a charging station, if you're charging the battery at a charging station, then this compatibility check is extremely important. There you have to ensure that the battery you are charging is compatible with the ratings of the charger which is present at the station. Okay, next part which we are trying to understand is the transmit parameters. So we are going to provide the charging parameters. We are going to speak about the charging parameters, wherein we tell, okay, this is the maximum output which my charger is going to provide. Then we are going to also talk about the maximum current which will be used for charging the infrastructure. So that would be there. All right, and then again it is going to be sent to the vehicle, and we are going to ask the question whether the vehicle is compatible with this rate of charging or not. Okay, so this is again very important, because if we don't take care of these precautions, then there is a possibility of the vehicle battery getting heated and getting damaged. So for that we have to check the rate at which the charging is going to happen and whether it is falling into the limits of the vehicle battery. So for that, compatible check at both the ends is important, at the charger as well as the vehicle end. Then the next part is to generate a start permission signals that is going to be there. Okay, and that would be recognized again by the charger. So K on and J on. So these are again there. Okay, so K on and J on. So these are definitely clear cut, visible in the next slide. After that, if the connections between the charger and the vehicle are locked, we are going to perform insulation test. We are going to perform insulation test. And if the insulation test is successful, we will be testing it with a test signal, obviously. So that test signal would be sent, and we are going to monitor whether the insulation test is happening satisfactorily or not. So once the insulation test happens satisfactorily, we are going to establish the BMS algorithm. In the BMS control algorithm, we are going to speak about the charge control method. Okay, here we will be continuously monitoring the temperature of battery, we'll be monitoring the current of the battery and the voltage of the battery. So these three parameters, voltage, current and temperature, would be monitored on real-time basis, and they would be monitored at different rates. So it typically it has been given as 100 millisecond, but it can be variable. It can be 10 millisecond or it can be 1000 millisecond as well. Okay, so it depends on the manufacturer. So that is there. Okay, now the charging control algorithm, it would be running continuously. We'll be monitoring the battery voltage, we'll be monitoring the SOC continuously, state of charging. Okay, and once the battery voltage reaches its maximum value, then we are going to generate a zero current signal, and by doing so we are going to stop the charging. Okay, so effectively we are going to have this kind of pinout. This is the pin layout. If you see that the pin number 5 and 6, they are having maximum diameters. Okay, the values are also shown. Typically, if it's around 42.4 mm square, then it can tolerate current around 150 amps, and if it is around 53, it tolerates current up to 200 amps. So this is something we need to understand. So pin number 5 and 6 are there, which are going to be playing actual, whereas actual electric power would be flowing. All the remaining are for the control signals. Okay, and we'll be monitoring the battery status, charging status, okay, compatibility by making use of the remaining pins. So this is something which I wanted to, introduce in today's class. So I suppose you have understood most of the contents in today's class. So that would be the end from my end. So if you're having any doubts, we can have a brief discussion in the remaining duration. Okay. So this was the content. So I hope you have understood. So we have covered the charging infrastructure. We have spoken about EVSE, and we have also talked about the standards in current Indian market. We have talked about GB/T, CHAdeMO, Type 1 AC, Type 1 DC, and the algorithm in which the battery is going to charge by any electric vehicle supply equipment. So yes, I'm open to your questions. Any question related to topologies, related to efficiencies, okay, then well to well efficiency, and the EVSE algorithms that we considered right now. Anything is fine.
No, sir, no any doubt.
Okay, fine. Fine then, that would be all from my end.
Uh, Thank you, sir. You just utilized your valuable time. And thank you from our institute.
Yeah, thank
And
you very much.
I declare this today's session will be concluded. Thank you.
Thank you very much.